So that's why the Friday class today I'm taking rescheduling it, and that's why the class has been set. I hope today network connection will be okay. Not many students have yet joined. Okay, so let me start sharing the screen. So as we have discussed in the last class, today we will discuss about the design of lintels. So lintels, as you know, these are the horizontal beam-like structure which are actually placed at the opening of any building. Means the opening could be your window or door. So the brick masonry that is constructed over the opening of doors or windows. So for that, a structure is necessary which will actually hold the load of the brick masonry above the opening. So for that, we provide the supporting structure in the form of a beam which is called lintel. So lintel could be of many type of materials. In earlier days, it was used of wood, even in metals form also. Okay. Nowadays, mostly RC beams are used as lintel, and even some hard stones are also used for decorative purpose. In your European countries, you can find a decorative form of lintels are provided and are kept open uh, for visual treatment. And so mostly lintels are provided as a load bearing structure, and they hold the sole purpose is to hold the masonry above the opening of the doors and windows of a building structure. So that is the difference between the beam, a normal common beam, and lintel. If someone asks what is the difference between beam and lintel, so beam, you know, they transfer loads of the slab, the loads that are coming on the slab, and finally the slab load is transferred to the beam, and this beam transferred the load further to the column and finally to the foundation. The only difference is that here the lintel is taking the load of the masonry structure, the brickwork that is above the opening. Okay, and it is simply supported. Okay, they are not fixed at ends, they are not continuous. Mostly they are simply supported, and they are held by the bearing. They rest on the portion of the brickwork that continues for the window, the opening, the portion that is open, the extra portion of beam that is extended, and from bearing action it simply rests, and this is how it works. And this is how it is different from a normal beam. So let me first discuss about the basics of how the load is transferred to the lintel. So what happens when the load in the form of masonry structure above the lintel, the load is transferred, is taken by the lintel itself. May not necessary that it will take the complete load of the masonry structure. Okay, so why? Because due to the arch action, okay, if some arch type structure is formed, due to some arch action, this load, some of the loads could be transferred to the bearing, and it may not, and the whole masonry structure load may not be transferred to the lintel. Okay, and this transfer of the load, the masonry load into the lintel, actually completely depends on the height of the masonry above the lintel. Okay, the height of the wall that is there above the lintel, that is carrying, that height actually determines that the form of load that will be falling at the lintel. The lintel will be carrying the form of load. We will see in the next slide how you just remember that due to the arch action, we know what is the arch. The all the horizontal and vertical forces, they are all transferred to the support, to the two supports and end supports, and there you won't find any in between force. And all the forces are transferred to the end bearing. So this is the arch action, and that is why not all the loads are actually transferred to the lintel, and some of the loads are transferred to the supports of the wall. And if you see the diagram, here it is showing the reinforced concrete lintel beam, and there will be bearing. Bearing means the portion of the wall on which the lintel is rested upon. Okay, that portion is bearing, and depth of the overall depth of the lintel will be known. Clear span is the distance of the opening of the door or window, that is the clear span, and effective span is the distance of center of bearing from the distance of center of the one bearing to another bearing. Okay, means the distance between center to center of the bearings is your effective span of the lintel. Okay, understood, I hope. So this is the concept. Next, let us see how the loads are actually transferred to the lintel. As you can see the two diagrams, see the first diagram, left one, a equilateral triangle is drawn, okay, on a lintel. So the condition is, for the transfer of load, if we draw a equilateral triangle and the length is equal to the clear span L. Okay, so equilateral triangle, all the sides of the length of the triangle is same. So all the total length is 3L, L plus L plus L. The circumference of this equilateral triangle, and interior angle of the triangle is what, 60 degrees. Okay, so if you draw equilateral triangle of this length L, means the effective span, and if you find the height of this equilateral triangle is H, and if you see that the height of the masonry wall that is resting on the lintel is more than 1.25 times of the height of the equilateral triangle. Okay, in that condition, the load that is coming onto the lintel is actually in the form of the equilateral triangle, the hatch line that you see. If the total height of the lintel above the lintel, above the opening of the lintel, above the opening there will be lintel, and above the lintel there will be masonry wall. So that height of the masonry wall, if it is more than 1.25 times of the height of the equilateral triangle, then all the loads that will be coming to the lintel will be in the form of equilateral triangle only. Okay, so we see that not the total load of the masonry wall is coming onto the lintel. Okay, why? Because of the arch action. Next case, on the right side, if you see diagram, if the same equilateral triangle for the same condition, if the height of the masonry wall, that is capital H, above the lintel, if the height of the masonry wall is less than 1.25 times the height of the equilateral triangle, then the the total load that will be coming onto the lintel will be in the form of rectangle. See the hatched line, it is the total, means the total size of the masonry wall load is coming onto the lintel. Okay, so this is the condition, this is a very important condition that you must know, that is necessary for to remember for the design of lintel. Okay, so what we actually see, it may seem strange that if the height is more, then what happens due to arch action, there will be the formation of the equivalent load will be in terms of triangle. But if the height is less, the arch action will not come into play. Instead of taking equilateral triangle, we have to consider the total portion of the rectangular portion of the masonry wall. So this is the condition. And if you see the total load that is transferred to the lintel, that is the area of the equilateral triangle, that is half into base into height. So half into L into the height of the equilateral triangle formula is root 3 L by 2. So root 3 L by 2 into gamma is the unit weight of masonry wall. So if you multiply, you will get the total load that is transferred to the lintel. And on the second case, the total load that is transferred on the lintel is actually length into breadth of the rectangle, that is capital H into L into gamma, the unit weight of brick wall, masonry wall. Okay, I hope. Yeah. Anush Kumar, I am Chakraborty, Ankit Kumar, Buddhadev Santra. Example, a simple example of the lintel, how to design it. So in the design example, let us see. Condition given here is that a lintel is to be designed .2 meter. Okay. Suppose the opening of a it is located centrally at 300 mm thick wall. Okay, wall thickness is given. The height of the masonry wall above the lintel. Okay, capital H is given, that is 3 meter. Is asked to consider 19 kilonewton per meter cube. Okay, the unit weight of masonry wall is 19 kilonewton per meter cube. All of you must remember this. And it has been asked to consider M20 grade of concrete and Fe415 steel. Okay, so to proceed, we first have to find out the effective length. Okay, because only the opening space is given, and FCK is given, Fy is given, gamma is given. So let us first assume that the bearing of the lintel wall means the length up to which the lintel is resting upon the walls. Let us suppose 200 mm from both the side, 200 mm left side, 200 mm right side. So what will be the effective length? Effective length is center to center distance of the bearing. So the clear span is 2 meter plus 0.1 meter from one side, 0.1 meter from another side. So total length comes as 2.2 meter. Fine. Next is we have to find the we have to consider the effective depth. So now the overall depth that is considered, and that is 200 mm, and let us consider a effective cover of 25 mm. So small d becomes 175 mm, and for this case will be 2.175. So from here we find that L effective is 2.175. Okay, because we have to take smaller of the 2.2 and 2.175. Now let us consider the load calculation. So for this we have to find the height of the equilateral triangle. So the formula for the height of the equilateral triangle is root 3L by 2. So root 3 by 2 into 2.175. So H is 1.88. Now we have to check that what is the value of 1.25 times height is. So 1. So here we see that the total height above the height is given as 3 meter. So we see that the capital H is more than 1.25 H, small h. So we can consider the load in terms of equilateral triangle only. Okay, since capital H is more than. Fine. Next is your total load. Total load of the equilateral triangle is to be find out. So the total load of the equilateral triangle is half into base into height. So half into 1.88 into 2.175 into gamma into the width of the wall, that is 0.3. So we get the value of W as 11.65 kilonewton. Okay. Now the maximum bending moment at the midspan is WL by 6. So using this, we find the bending moment that is required for the dead load. Next is to find out the self weight. The cross sectional area into unit weight of concrete, that is 25. So 0.3 depth into 0.25, 0.2 width into 25. So omega is 1.5 kilonewton per meter. From here we will find the moment due to self weight, that is WL square by 8. So W into 2.175 L square by 8. So we'll get 0.9 kilonewton meter. So now the total moment means the moment due to maximum bending moment at the midspan and the maximum bending moment due to self weight, that is 4.27 plus 0.9 self weight is 5.13 kilonewton meter, and we have to multiply this with the factor of safety, and so the ultimate moment turns as 1.5 into 5.13 kilonewton meter. Okay, so up to this much is the calculation part that is different from any simple beam for a lintel, and the remaining calculations are same. For now we will design like all the values, the mu, the factored moment is been find out, and from here we can proceed as a simple beam that is designed, a singly supported beam, how it is designed we can design. So first we have to check the depth that we have considered. So depth required, we know it is root over of mu by RUB. So this value of RU that is find out from the equation for Fe415 and M20. The equation you know for RU. So putting all the value, we get D required as 97 mm, and which is less than 175 mm the effective depth. So it is okay. So minimum depth required condition is fulfilled. Next is the area of steel. So for the area of steel, we know the formula 0.87 Fy AST D into 1 minus AST Fy by FCKBD. So putting all the values where the AST is unknown and putting the value of mu, we will get the value of AST, that is 124 mm square. Now considering a 10 mm bar, the number of bars required will be obtained, that is 2 number of bar. Next is the minimum area of steel. Okay, so minimum area of steel is 0.85 BD by Fy. So here we have seen that it is coming within limits. The obtained value is more than 107 mm square. So it is okay. The design is okay. So we can provide this 10 mm bar 2 numbers. Next is shear design. So for shear design, the maximum factored load for the wall portion above the lintel and the self weight of the lintel is required. So W by 2 plus WL by 2. So from here V is obtained, and factored shear design for factored shear force, there is we have to multiply 1.5 factor, and that is 1.5 into 7.5, 11.25 kilonewton. So tau V is equal to VU by BD. So from here value of tau V is obtained. Next, PT is to be required to find out. So the value of PT, we know it is to be obtained from the design table for 100 As by BD. So from here, table 5.1, this table is given in your IS code. Okay, table 20 most probably, and from here we will For our grade of concrete, we will obtain this value of 100 ASPD. So for here, for the PT value 0.3 M20, by interpolating the values, we will get the value of tau C, that is 0.384. So we see that the value of tau C is more than tau E. So from here we can conclude that no shear force, no shear reinforcement is required. No extra reinforcement is required for counteracting the shear. So using 8-5 bars of two-legged stirrup, so we have to obtain the spacing of the stirrup. Spacing formula is 0.87 Fy ASV by 0.4 B. So from here we obtain the spacing of stirrup as 302 millimeter. And maximum spacing permitted, we know that we have two conditions. B, so providing two legs 8-5 stirrup of 130 mm center to center distance throughout the length of the lintel, and we also have to provide two numbers 8 mm dia anchor bar at the, okay, zone and tension zone. We can provide two numbers of at the tension zone 10 mm bar, and at the compression zone for anchorage 8 mm bar is to be provided, and two leg 8-5 dia stirrups are to be provided at a distance of 130 mm center to center. If you increase the dia, then obviously you will have a longer spacing between them for the stirrup. Next step is to check for the development length at support. So for condition when there is no curtailment is done, suppose 1 is 717 is already obtained 11250 Newton. So for development length of this 10 mm bar, that is 0.87 Fy5 by 4 tau BD, from here we obtained as 470 mm. Development length is 200 by 2 minus 25, that is 75 mm. Now equating this for the value LD, that is less than equal to 1.3 M1 by V plus the assumed value of the bar straight bar. So equating this, we obtain the value as 965 mm, which is more than 470. So the length of 75 that is assumed without any hook, the straight bar is okay and within the limits. Okay. So after that, finally, after the design, we can draw the lintel, the cross section, the longitudinal cross section, and cross section of the lintel. So the bearing is 300 mm as shown with hatched line, two sides, and the clear span is 2 meter. The height is considered, the total overall height of the beam is considered 200 mm, and two numbers of dia 10 mm at tension zone, and two numbers dia 8 mm at the anchorage, as the anchorage bar is provided at the compression zone, and two legged stirrups are provided of 8 mm 5 bar at a distance 130 mm center to center. So this is how after the design you have to draw the L section and the cross section. The cross section has to be provided by cutting the section of L. You can provide section AA or XX section. See, the width of the lintel is considered as 300 mm and the depth is 200 mm. So I'm giving you a problem. Also try to solve it